Yeah, so we're CytoSMART. We're originally founded in the Netherlands as a startup at the University of Eindhoven 9 years ago. Next year, 10 years. What we do, basically, we combine three areas: AI, image analysis, cloud computing, and miniatures microscopes. And we try to do that in order to build a low-cost, affordable, label-free, long-term quantitative microscope solution. We have a bunch of different products that we've been selling for the last 10 years, 9 years. Small incubator cameras. So these are fixed cameras that go in the incubator, automated cell counters, and live cell images. I'm just going to pick out a few today and show you a couple of examples of what we can do. The main benefit of our systems is that they're very small. So they've got a very small footprint, which allows you to run experiments for a long time without disturbing your colleagues, as you can see in the picture on the right. So here's a basic example of two incubator fixed microscopes that run two films, basically, of cells under different conditions. And then we can analyze the migration of these cells, relatively straightforward. Here's another example doing the same thing on, I guess, a drug that inhibits growth of one cell line. And as you can see, it's live cell imaging, but then very straightforward. Okay, so these were simple systems. We have a more advanced system, which is a scanning system, and that's a CO2 incubator-proof system. So it goes inside CO2 incubator. It's designed to match the airflow of the incubator, and it can take loads of images, and it's very robust. So what it does is it scans a plate in a continuous motion and records about 9,000 images per scan. And it can then take these scans every hour. And because it's relatively low energy consumption, it can do so for a long time without disturbing the cells, for example, by heat or phototoxicity. One of the main differences in our approach compared to more traditional automated microscopy approaches is that we take a total area. So if you look at a simple confluency readout, for example, the picture just showing you that the confluency in this case of this well is not homogeneously spread across the well. So depending on where you take that measurement as a point of interest, you get a different readout. If you measure the total well, you don't have that problem. What we do, basically, we take with a 5-6 megapixel camera, we take 9,000 images. That's a lot of plastic sometimes. Then with the image analysis, we detect regions of interest. So in this case, that will be the wells of this 24 well plate. And then within these wells, we can detect things of interest, which can be static things or dynamic things like movement. Also, this product has a very low footprint. So here you see a picture of a customer that I think has a lot of colleagues. So I just wanted to run you through a couple of examples. We've got different ones depending on the image analysis being used. So clonogenic assays, wound healing assays, basic proliferation assays of cell competency, but also organoid stuff looking in the matrigel domes and moving objects like cardiomyocytes. If this works with sharing my screen, I'm just going to show you a couple of examples. You should be seeing CytoSMART Omni Cloud page with a, what is it, 12 well plate. Is that what you're seeing?
Yes, we do.
Okay, so these are 9,000 pictures at one time point, so T is 0, and I can zoom into that, and then I can see the individual cells at cellular level, and then we can run image analysis on that, in this case to detect the scratch area. And because this is a time lapse, we could do so over time. So as you can see, it's decreasing and finally it's closing. And we could make this movie for any part of the well, anywhere, right? And then you get the data points of each well. So if I give you another example, this is a proliferation example. Let's turn up the brightness a little bit. So here you zoom in, you can see the individual cells of every position, and then with image analysis, we can detect the cells, and we can look at how the cells in this particular flask start growing and ultimately fill the whole flask or whole well. And then if we map that, you get these confluence data. I tried to take a nice example for this occasion. This is a more advanced image analysis question, I guess. This is a clonogenic assay. So if you zoom in here, you see at T is 1. Hopefully you see a few clones. Don't know how much compression you've got. And if I'm gonna move forward, you'll see these clones growing over time until probably it's full completely. With the image analysis, we can then detect the clones in each well. I hope Zoom allows me to show this. So hopefully you're seeing orange circles around all these clones. And then you can map that over time, giving you these plots of different drugs. So in this case, it's loxorubicin, I guess, different dosages. So going back to the presentation, also wanted to include a couple of recent examples where we think this approach of light-cell imaging can be beneficial. So this is a case where people are culturing organoids in matrigel domes. And the problem with that is that the domes are too big for a conventional field of view, and the objects of interest are too spread out through the dome, which is usually several millimeters in height, to work with a normal confocal system. So what we've done is we've taken images of these, and then we've trained a machine learning network to calculate the blurry and not blurry and organoids that are maybe overlapping. And then we can plot how these organoids are developing in these domes. I'll just try to show you a picture of that, how that looks. So here you see the image analysis of matrigel, organoids in matrigel. And as you can see, the AI is quite capable of detecting these organoids, although some of them are not in focus and other ones are in focus. So we've estimated with 3 customer groups right now, this is running already in several labs, that we can do about 70–80% of all the organoids in such domes. And I think in general, there are multiple domes in each well. So yeah, this looks to be quite promising. And what you can do with that is optimize medium or feeding strategies for these organoids, but also do drug testing, looking at shrinkage and number of organoids. As you can see on the picture on the left, it's pretty crowded in some of these customer examples. But the image analysis seems to cope quite well. I'm going to show you another example. This is actually taking fast frame rate movies in a 384 plate of cardiomyocytes. So here you see a patch of cardiomyocytes beating. It's a very gentle beating in the middle, so I'm not sure if you guys can see it. And here on the right, you see the image analysis measuring the spatial contraction of these cardiomyocytes. And as you can see, they're not beating in the same strength, same amount of movement everywhere. So what we can do next is plot this, and then you get a graph of the relaxation time and frequency of beating. And we can do that with different stress factors, different drugs, and so on. So that's my presentation. I tried to keep it short.